In the previous video, we talked about the descriptive statistics of bivariate data. We talked about correlation coefficient and the scatter plot. Now let's do something more quantitative. Let's talk about regression analysis. Here we go. Based on the data set of problem 1, the first problem, which is given again here, find the best point estimate of the volume of the foam when the temperature is 65 degrees. Nothing is accurate in statistics. Nothing is absolute. Everything has an error. Everything is an estimation, but not every estimate is the same. There is better estimate, and there is worst estimate, and there is the best point estimate. That's what we are trying to find out. And if you estimate incorrectly, then the real values tends to be lower than that rather than higher, or vice versa, higher than that rather than lower. The best point estimate, errors do happen, but either higher than that or lower than that, that are kind of spread out and cancel each other. That's what it means by the best point estimate. It doesn't mean it's really the accurate one. Nothing is accurate. Nothing is absolute in statistics. Now, how do we find out the best point estimate? I advise you to use this formula here. Let me expand the font a little bit. Yeah, this one. Our textbook has a different setting. It gives you two formulae, as a matter of fact, 3, and some step-by-step process to get those. I'm afraid that's too complicated. I think it's going to be much more effective if you rely upon just one formula here. And this is based upon an equation of the line. An equation of a line, kind of like this. Y equals mx minus x naught plus y naught. If you have taken intermediate algebra rather recently, then you'd probably remember this is a slope point equation of the line. Slope is m, and running through the point x0, y0. Through the point x0, y0. And exactly the same thing is going on over here as well. The line is running through x bar, y bar. X bar and y bar are the means, so it's pretty reasonable. And the slope is this one, r sy over sx. Now, please don't ask me why, because the derivation is rather complicated. It requires multivariable calculus or something far more advanced. All you have to do here in this level is to plug in the numbers at right place. This problem is asking you to find out the best point estimate, y value when x is 65, so x value is 65. All the other things are the mean, standard deviation, and correlation coefficients. Put those in, do the computation, and you get 380. Oh, by the way, if you stop here, 379.2 something, I'm not going to take off any point. But I prefer to have 380 because all the volumes here are in, almost all, except for this one. Almost everything here is in 0 in the last digit. They're all in tens. So it's gonna be better if you round up to 10th digit, especially considering this is 7-9. It was an easy call. Now, justify this computation through an appropriate plot. This is an extra credit part. Now, how do you justify and what kind of plot? There can be some different ways, but the most preferred way is this kind of regression line along with the scatter plot. Scatter plot is the same thing you saw before. We have black dots here, and the red line is the regression line, the line of best fit. The green point here is the mean point, x bar comma y bar. And if you start from x equals to 65 degrees here, okay, go up and hit appropriate point in the graph, and then move horizontally, excuse me, and read the y-coordinate value, 380 degrees. Now, if you don't have this dotted arrow, that's fine, as long as you have scattered plot and the regression line. There could be some other kind of justification, graphical justification that I cannot think of, but well, I take it back. This is the only justification that I can think of. Okay. Next problem is actually going backward. Best point estimate of the temperature this time when the volume is 380 milliliters. Wait a minute, didn't we just do that before? 380 milliliters. So if I go back, hey, it's gotta be 65 degrees. No? No. The answer is no. We have something called regression effect. Each time we run regression, the answer will approach a little bit toward the mean each time we do. As a matter of fact, we have this kind of computation. Let me expand this font a little bit again so that you can see this thing better. Compare this regression equation and that regression equation. Exactly the same, except x became y and y became x. Why? Because this time y is known and you're looking for x. That's why we are switching x and y. We're simply renaming them. So if I do that, well, y is given at 380. Otherwise, plug in all those mean and correlation coefficient and standard deviations and so on. Do the computation, you get 67.6. Not 65, but a little bit closer to the mean. Now, if you start from 67.6 and put it over here, right here, and run the computation, you're gonna get something bigger than 380, a little bit closer to the mean. Now, finally, this is a graphical justification. The blue line is a regression line when you're looking for x value. Start from 380 and then move horizontally to hit the graph and go down and read your x-coordinate value. You're going to get 67.6. This blue line and the previous graph, the red line, are not the same. These are not the same. Well, if you look at one after another, you can see that these two lines are a little bit different. Blue line is a little bit stiffer. Red line is a little bit flatter. These are two different lines. If these two had been the same, start from 65 to 380, 380 will come back, right back to 65. But these two lines are different. We have two different formulas. Start from x, looking for y, we use this one. Start from y, looking for x, we use that one. This is the red line, and that's blue line. Consequently, we have a little bit different result. Start from 65, instead of coming right back to 65, a little bit bigger. We came back to about 67.6. You're looking at so-called the regression effect.